Okay, what I thought was really interesting is that they use a property here on part F that they don't add to the properties up here. So we'll go ahead and solve through a couple of these using these properties, and then we may add our own up there that's necessary to work part F. So let's take a look at these. So just a quick review. We know that the sum of logs is the log of their product, and I like to say that in my head when I do those. The difference of logs is the log of their quotient. The positive terms are always multiplied together in the numerator, and the negative terms are in the denominator multiplied together. So if there's a whole string of them, that's how we differentiate. Since this is the positive term, it's in the numerator. Since this is the negative term, it's in the denominator. And then if we have an exponent, we can bring it out front. If it is out front, we can bring it back as a power on the base that's on the number that we're taking the log of. So an example of each of those is just given right here. So the sum of logs is the log of their product. So 5x can be split either way. So you can split it apart to log base 2 of 5 plus log base 2 of x. Or if it is split, then you can put it together as the product. If it is written as a quotient, you can split it to the difference of logs. And if it is written as a power, you can bring that power out front to try to get it by itself. Okay. All right. So let's run through some solving with those properties just for a little refresher. Now, the important thing to remember with all of these properties is they do require that you have the same base. You have to have the same base throughout. So if you ever don't have the same base, you would have to use change of base properties before you could use these properties. So just want to point that out, that they always need to be change of base, the same base. Okay, so for this first one, that's a sum of logs. So that can be rewritten as log base 4 of xy, just the log of their product. Okay, difference of logs would be the log of their quotient. So log base 3 of 5 over z. That copy quality is really bad on this input. Okay, and then we have a whole string of them, and they're all log base 10. So I know that's going to be the log base 10 of, and we said every positive term will go in the numerator. So we've got the x there that'll go in the numerator, and then we've got a 5 and a z that both have minuses in front of them. So they'll be multiplied together in the denominator. So that's over 5z. Okay. All right. Now we have a coefficient out front. So what are we going to do with that? As a power, and we have a difference of logs. They're all log base 2, so it'll be log base 2 of, as soon as I see that minus sign, I know I'm going to have at least something in the denominator. My numerator will be x cubed, and my denominator will be y. Okay. All right, on this next one, same kind of thing. Let's try that on your own, and let's see how you do. We want to bring the coefficients up as powers. And then we've got a difference and we have a sum. Is that what you got? Still working? Is that what you got, McKay? Very nice. Okay, now F is the one that I said uses a property that they don't put up here. And it's not a property that you probably used last year. It was a property I had to look up. It's not one that I've used often. So let's go ahead and talk about it. So here they've got 2 plus log base 6 of x. And at first I thought, oh, that was a typo, but it's not a typo. They want you to convert a plain number to a logarithm. They want you to convert a plain number to a logarithm. Did you guys do that last year? Like I said, I don't think we usually do that. Okay, so let me show you how to do that. So we're just going to think of 2 as 2 times 1. Do you agree? Okay, so remember in math, this strategy of using a well-chosen form of 1, it's a super popular strategy used throughout math when we need to get something into a form that we can work with. So you guys agree that it's 2 times 1, and I'm just going to copy the plus log base 6 of x. No changes there yet. Okay, so the well-chosen form of 1 that we want to use is log base 6 of 6. Log base 6 of 6. Now I'm still going to add this other log base 6 of x over here. So no changes. So the only change I made there was substituting log base 6 of 6 for 1. Do you guys agree that log base 6 of 6 would be 1? Remember, the answer to the log is the exponent. So we're saying what power would we raise 6 to get 6? And what power would we raise 6 to get 6? The first power. So the answer is the exponent of 1, and so that's why I could substitute it in for 1. Okay, now do you see what they can do? Yeah, Elena sees it. So if I just rewrite this without the parentheses to make it a little more clear, that's 2 times log base 6 of 6 plus log base 6 of x. We'll just bring that coefficient back now as a power. This is the sum of logs. So that's going to be the log base 6 of 6 squared is 36. And we're going to multiply them together, the product, since they're added. The sum of logs is the log of their product. And that is what it's equivalent to, which I thought was very nice. Okay, so since any questions on that? Are we doing okay with that? Okay, let's go back and try to formalize that and add that up here to our properties so we can kind of think about that. So if we have a constant, let's just add it up here. If we have a constant, I'm like, where to put it? We'll try it right here. If we have a constant, so I'll put k for a constant. That equals k times log base b of b. Okay, so where b is our base. So that equals log base b of b to the k. Okay, so that's just writing it there so we can remember it, so we can go back and look at it and remember it. I really did think it was funny that they just like didn't even mention that or review that, and then they used it, and it's a property that we almost never use. But might be because more than a property, it's an algebraic strategy of using a well-chosen form of one to get something into another form. So I think still it's worth mentioning, it's worth formalizing. Okay, so which of the following expressions is equivalent to log base 3 of x squared divided by y? Okay, I see that fraction bar, so I know I'm going to have a difference of logs. That 2 I know can come out front, but it can only come out in front of the x. Do you guys see the correct answer there? The correct answer is C. The correct answer is C. It's not 2 times x, it's x squared. The 2 has to be out in front there, but not in front of both terms, only in front of the x. Okay, there's a million things that you can do that are wrong. The correct answer there is C. Okay, so it says the function f of x equals log of 6x is a horizontal dilation of the function g of x equals log x. Show that f can also be written as a vertical translation of g of x. So we're just going to use our log properties to rewrite this. So do you guys agree that multiplying by 6 is a horizontal translation inside there? Okay, so if they're saying we can rewrite it as a vertical translation, which means we need to have, they specifically want it in the form of g of x plus k. So they just want a constant out front there. Okay, and so let's go ahead and see if we can do that. Okay. So log base 6 of x, it's just a product, so we can rewrite that as f of x equals the log of 6 plus the log of x. So we can just split it to the sum of logs. And since the log of x equals g of x, then that just equals log of 6 plus g of x, which equals g of x plus k. Right here, they define g of x as the log of x right there in the problem. Okay, so g of x equals g of x plus k, where k equals the log of 6. Remember that the answer to that log is an exponent, which is just a constant. So that is a constant. So there we're just saying it's just that plus constant, just a little bit of manipulation there. Okay. Oh, wait. Scrolling down. All right, change of base property. Remember that you can change to any new base, and it turns out that log base b of x equals the log with the new base of what you were taking the log of over the log with the new base of the old base. So I always remember that the base is down low, and so it's what goes to the denominator. So you're still taking the log of what you were taking the log of, only with the new base. over the log with the new base of the old base. Okay, so that's definitely a property we want to remember. And it says right here, note this property illustrates that all logarithmic functions are vertical dilations of each other. Okay, so we just showed how a horizontal dilation could be a vertical translation. So how can a change of base show that all logarithmic functions are vertical dilations of each other? Can you do that algebraic manipulation to see that real quickly? So let's try writing that out. So that means that the log base b of x is equal to, if we're looking at this property right now and we bring that out front, that would be the 1 over the log base a of b times the log base a of x. Now remember that logs are just constants, so this is just a constant times log base a of x. So log base b of x is just a vertical dilation of another log. So can you see that? Yes, no, maybe so. All right. So I think I just thought it was interesting because they just said it there without showing the algebraic proof that it does. So I thought we'd go ahead and show where it actually does. Okay, so it says let f of x equal log base 4 of x and g of x be log base 9 of x. Okay, so the first thing I noticed is that they've got different bases. Show that f is a vertical dilation of g by finding the value of k such that f of x equals k times g of x. So let's give that a try. Okay, so show that f is a vertical dilation. So we want to show that f of x equals k times g of x. Okay, so if we take our g of x, log base 9 of x, and rewrite it, and I think we want to do it the other way. Yeah, so f of x equals log base 4 of x. And if we do a change of base to that to get it to be log base 9, then that would just be log base 9 of what we were taking the log of. It's a 9 now, over the log with the new base of 9 of our old base, which was 4. So we just use change of base to get it to be base 9. And then we just bring that separated out front. So that's 1 over log base 9 of 4 times log base 9 of x. And again, we said that log base 9 of x is g of x. So that's just 1 over, well, we'll go ahead and write it in that form. 1 over log base 9 of 4 times g of x, where k equals 1 over log base 9 of 4. So you could rewrite that as k times g of x. Because that's just a constant. So using those properties. Okay, so we did it with letters here in pink, and then we did it with numbers there in red. So the same process. Okay, natural logarithm is just a log with a base of e. So log base e of x is rewritten as natural log of x. Which of the following expressions is equivalent to 3 times the natural log of x minus 4 times the natural log of y? So use your log properties. That's a difference of logs. I've got coefficients that I need to bring back up as exponents. Okay, so which one of those looks right? It's definitely going to be A, natural log of x cubed over y to the 4th. Very nice. Okay, so that is our content for 2.12. Today on the board, we're doing 2.12 and 2.13. So that was 2.12. Moving into 2.13, we're doing solving exponential and logarithmic equations and inequalities. So we're going to do a lot more math today, so it feels more like a math class today. We're going to be solving equations and inequalities. Here's a quick review of your exponential rules. We've already reviewed those, but they're nice to have there all together. And about switching from exponential form to logarithmic form, which we're also very good at. Okay. Here, just a little note about vocabulary. It says the argument of every logarithm must be positive, meaning it has to be greater than 0. So in the argument, in case you're wondering what that is is the number you're taking the log of. So that's your argument. Okay. And they said that's because your base always has to be positive. Your base always has to be positive. And so we can't raise a positive number to a power and get a negative number. And so our argument has to also be positive. We mentioned that last class as well, I believe. Okay, so equations with only one log or exponential function. If an equation or inequality involves only a single logarithm or only a single exponential function, we can solve it by converting between exponential and logarithmic forms. So we're going to isolate the exponential or log expression on one side of the equation and have a number on the other. And then we're going to write the equation in the alternate form. So if it's an exponential, we'll rewrite it in logarithmic form. If it's a log, we'll rewrite it in exponential form, solving for the variable if necessary, and simplify and round as directed. So let's solve a few basic equations. 4 to the x minus 2 equals 7. So we've got to first get that exponential term by itself. So we're going to add 2 to both sides. So we get 4 to the x equals 9. Okay, then we're going to rewrite it in the other form. So this is an exponential, so we're going to solve for that variable by rewriting it in logarithmic form. Can you help me with that, Elijah? What should that look like? Log what?
Log base 4.
Of. Beautiful. Okay. And that's what I said about most of you will be comfortable just going straight to it, just thinking about it. But that is exactly right because we said 4 to the x equals 9. There's that disco dancing to check yourself. Okay. All right. And we didn't have to solve any further because that already had x solved for it. And that's why it said if necessary. All right. Let's try another one. Again, only one exponential expression. So we're just going to isolate it by subtracting 5 from both sides. So 2 to the x plus 3 minus 5 makes 21. Okay, and then we're going to rewrite it in the other form. So we would rewrite that in logarithmic form. Do you want to give that a try, Sana? Okay, what would that be?
Log base 2, 21 equals x plus 3.
21 equals x plus 3. And this time we do have to solve for x. So we'll go ahead and solve for x by subtracting 3 from both sides. So x equals log base 2 of 21 minus 3. It's separate out there at the end. That might be careful. Notice here, I did put the parentheses around the 21 to emphasize it's only the log of whatever's closest to it. Even if I didn't put it, it would be whatever's closest to it if it's not in parentheses. But it's often very helpful to your readers to go ahead and put a parentheses to emphasize what you're taking the log of and what you're not. So we were literally just subtracting 3 from both sides, so it's outside of the parentheses there. So be careful on that, okay? All right, let's try, and we're leaving these like this. We're leaving them in exact form right now, okay? All right, so let's try that. Do we want to try another one? We will because it's E. Okay, we are not going to have to do all the practice today because there's a bunch in here, but let's go ahead and do this one since it's space E. Kaya, can you help me with this one? What should we do first? Or what would you do? Okay, so that's going to give me negative 10 equals negative 4 times e to the x, okay? We'll divide by negative 4 because we want to get rid of the 4 as well. So that's going to give me negative 10 over negative 4 equals e to the x. Okay, those negatives cancel. That simplifies down to 5/2. Okay, so that gives me e to the x equals 5/2. And now that we isolated the exponential expression, we're ready to rewrite it in logarithmic form. So Sid, can you help me with that? What's that going to look like?
Natural log of 5/2 equals 6. Of base 5, or base e of 5/2 equals 6.
Okay, so you were right to just say natural log because natural log means that it's base e. So natural log of 5/2 is x. Natural log of 5/2 is x. And we don't have to do any extra solving that time. We're in good shape just like that. Let me know if you have questions, okay? I know we're kind of doing this quickly, but as we must, okay? All right, then it says, solve the following equations, leave your answer in exact form. Okay, so this time we're solving logarithmic equations where there's only a single log. So again, this is problems that only have a single log. So we want to isolate that log by itself, and then we'll rewrite it in exponential form to finish solving. So let's go ahead and try that. So if I want to get this log base 3 of x plus 3 by itself, I'm going to subtract 4 from both sides. That gives me 2 times log base 3 of x plus 3 equals 6, just subtracting 4 from both sides. Then I want to divide both sides by 2 to get rid of the 2 out front. So that's going to be log base 3 of x plus 3 equals 6 over 2. I guess I'll show the division. I'll show the division there. 6 over 2 is 3. Okay. And then I just want to rewrite it in exponential form. We've now isolated our log, have the numbers on the other side. So now we're ready to do our disco dancing. 3 to the third power plus 3. Beautiful. Equals x plus 3. 3 cubed is 27. So 27 is x plus 3. Subtract 3 from both sides, and we get x equals 24. Follow-up questions on that one? Okay, let's try a couple more just real quickly. Let's do C. So we'll skip B, but it's a good problem, and if you want to go back, it's in your notes, you can do it. Let's try C. So we want to get that expression by itself. Okay, so the first thing we want to do is multiply both sides by 5. That's right, to clear that denominator. Sorry, I'm touching this screen. Okay, so the natural log of 2 minus x equals 5. Okay, so now we've isolated our log, so we're ready to rewrite it in exponential form. Maria, do you want to help me with that? What will that look like? What's my base if it's a natural log? E. Perfect. That's that disco dancing. E to the 5th equals 2 minus x. Now this time we do have a little bit more work to do to finish solving for it. I'm going to add x to both sides and then subtract the e to the 5th. So I get 2 minus e to the 5th. And we're leaving it in exact form. Okay, so not too bad. It's nice to actually just be doing some kind of regular equations. I think the log properties, exponential properties, I think those are kind of fun to play with and work with. So hopefully you'll enjoy solving those equations as well. All right, so equations with multiple logarithms, okay? So when working with more than one logarithm, we can use our log properties to simplify expressions before solving equations or inequalities. For equations or inequalities, because we're going to do both today, with multiple logarithms, we'll generally simplify to one of two forms. We'll either get the log on one side with a plain number on the other, okay, because sometimes we can get it in that form, or we'll get it to where we have a log on one side equals a log on the other side. Now notice this is when we have the same base. Do you guys remember solving any of these equations last year? Did you do any that were this hard? No? Okay, then we'll talk about, well, here it's about to tell us. Let's jump down here. Let me go ahead and tell you. Here's the strategy. What we're going to do when we can get it equal to two different numbers, the log base a of x equals the log base a of y. If the log base a of x equals the log base a of y, what must be true? X must equal y. X must equal y. So if our number, whatever it is raised to the same power to get us back to the two numbers that it gets us back to must be equal to each other. Those numbers must be equal to each other. So you are not doing an operation that gets rid of those. You're using logic to say if the log base a of x equals the log base a of y, then x must equal y. That's just a logical statement that lets you drop the logs, okay? So that's what we're going to do if it's form 2. If it's form 1, we're just going to rewrite it in exponential form like we just did on the other ones, okay? So those are our two basic strategies. All right, now a couple of important notes, and these are important. In either case, we need to check for extraneous solutions. Logs have restrictions. Logs have restrictions. Remember, we just talked about our base has to be positive and the number we're taking the log of has to be positive. The argument has to be positive. Okay, so we're going to be careful that when we plug x back in, our base is positive and the number we're taking the log of is positive. Okay, using log properties can sometimes lead to solutions that are not in the domain of the original equation. So we'll check those. Important note number 2. Now remember I said in this form, we were not doing a mathematical operation that let us drop the logs. We were saying logically, if log base a of x equals log base a of y, then x must equal y. Okay, so the log of x plus the log of y equals log of z does not, this is a common mistake, equal x plus y equals z. That's not true. That's not true. We have to use log properties to simplify this. We can't just cancel out the logs. This was a logic step, not a mathematical step, and it's only when you have a single log with the same base equals a single log with the same base. Now, what could we do with the log properties here? What's actually true here? What is the sum of this logs? That's the log of their product, the log of their product equals the log of z. And now, what can you tell me? That's right. Now we can drop the logs and say if the log of xy equals the log of z, then xy must equal z. Okay, so we do have to use those log properties to get it down to a single log on each side with the same base before we drop the logs. Okay, super important note. Don't forget either one of those. Extraneous solutions and has to be a single log on each side. Okay, so let's try some log properties, some log equations. All right, we've got multiple logs, so we're going to try to simplify to a single log on each side. The right side already is a single log, so let's see if we can get the left side to a single log. That's the sum of logs, so that's going to be the log of their product. So I'm going to go ahead, you can write it as 3 times x plus 4, or you could distribute it. It would have been okay if you had done it in either form. I'll go ahead and write it not distributed in this first step. Okay, and now what must be true? Right, the arguments must be equal. So now I will go ahead and distribute that. 3x plus 12 equals 5x minus 2, and then we'll just finish solving that. So that's going to give me 2x equals 14, so x equals 7. Okay, now be careful. There's 2 ways you can approach this to make sure that you remember to check your log equations. The first is to check for the domain restrictions before you even start working. And the second is to check your final answers before you box them and walk away from them. When you're solving for equations where you have single answers, it is much faster to just check your final answer. But you have to remember to check your final answer. If you get in the habit of looking at your domain restrictions first, I think that will help you to always remember, but it's a lot more work. So I recommend on an equations just checking your final answers. So let's do that real quickly. If I plug 7 in for x, the first one there's no x. In the second one, 7 plus 4, is that positive? Yes. On the other side, 5 times 7 is 35 minus 2. Is that positive? Okay, so this one is answer checks and is okay. We can include it. It's in the domain. Okay, so I'm not going to show you looking at just domain restrictions until we get to the next page where we're doing inequalities, or in a page or two when we're doing inequalities. Okay, but we could have done that here, and you'll see what I'm talking about in just a second. All right, so let's try this next one. We've got a difference of logs, so that's going to be the log of their quotient. Okay, the answer we get when we divide, the positive term goes up in the numerator, the term with a minus sign out front goes in the denominator. Okay, and now what must be true? Yeah, their arguments must be equal. So x plus 1 over 3x minus 5 must equal 7. If the natural log of x plus 1 over 3x minus 5 equals the natural log of 7, then x plus 1 over 3x minus 5 must equal 7. Now we do have some algebra to do to finish solving that, so let's show those algebra skills and knock this out real quickly. I'm going to multiply both sides by the denominator. Those are both divisible by 4. 9 over 5, is that what you got? Okay, now we cannot box that answer until we check. So that's the thing. You've got to remember to either check at the beginning or check at the end, but you've got to check. So let's see. If I plug 9 over 5, so 9 over 5 is just under 2. Do we agree? It's just under 2. So almost 2 plus 1 is positive. 3 times almost 2 is almost 6. Is almost 6 minus 5 positive? Yes. And then there's no other x's, so that one does work. It is okay, but we have to check it. Okay. All right. Do we need to do another one of those? I don't think so. We'll skip C. D is natural log, but it's still, do y'all want to do natural log since the base is different? It's the exact same. D's just like, no, we got this. Okay. And it wasn't just you. Maria agreed. She's like, no, please, no. All right. Let's see what we got. All right, so let's take a look at, but you're going to remember to check your answers, right? Oh, and I guess that's why we need to do C. Let's do C real quickly because so far all we've seen is ones that work. So that's a little bit of a spoiler alert, but let's go look at C real quickly just so you see what I'm talking about, okay? All right, so you guys said you didn't need to practice. You're pros at this. This is sum of logs, so it's going to be the log of their product. So log base 3 of x plus 2 times x minus 3. Equals log base 3 of 14. So what must be true? The arguments are equal. That's right, the arguments are equal. So x plus 2 times x minus 3 must equal 14. So far, so good? Everybody with me? All right, now let's go ahead and distribute that on the left so that we can combine that 14 with it and then factor it and solve it again. Okay, so just use those algebra skills. So that's going to give me x squared. 2x minus 3x is going to be negative x. 2 times negative 3 is negative 6 equals 14. I'm going to subtract 14 from both sides. I get x squared minus x minus 20 equals 0. Okay, and so that's why I distributed it, was so that I could go ahead and bring that 14 over and combine it. And now to finish solving it, I need to go ahead and factor it again. So factors of negative 20 with a difference of 1, that's going to be, I heard you, good, I agree, negative 5 and positive 4. Okay, and so that means x equals, we've got a set of answers, negative 4 and 5. But before we box that and walk away, we've got to check our answers. If I plug in negative 4 plus 2 is negative. And so right away I have to eliminate it. I don't have to check it anywhere else. If it fails in any of the places, it fails. And so if there is one where there's a plain X, always check that first, okay? Now, by the way, we don't automatically eliminate negative answers. Sometimes you're plugging in the negative and the expression will still be positive. So that's a common mistake too, is to just automatically eliminate the negatives. Sometimes negative answers are okay, and sometimes positive answers get eliminated. So you do have to literally plug it in and see if it works. If I plug in 5 plus 2 is positive, 5 minus 3 is positive, and so 5 does work, and so my answer is only x equals 5. Rishi?
If like your argument ended up being 0 when you plugged it in, would that work?
So it can't be 0 because you can't raise a positive number to a power and get 0. It's got to be strictly positive. Okay. All right. So now let's go on to the next page. I feel like I'm turning the wrong way, maybe. Number 4. So many problems. Okay, so this says solve the following equations, checks for extraneous solutions when necessary. So this is more of the same. Do you guys feel okay with this? Yeah, this is mostly just algebra. You'll be fine. But it is good practice, so if you want more practice, by all means, come back and let's do these problems. Okay, so let's look at number 5. It says, let f of x equal the natural log of x plus 10 minus the natural log of x. Let g of x equal the natural log of x plus 3. Find all values of x where the graphs of f and g intersect. So what are we looking for? Where the two equations are equal to each other. So we're going to set them equal to each other. Remember when we've been using the calculator to solve for the function's 3,000 or something? We put 3,000 in one side and the equation in the other, and we look for where they're equal. So where they're going to intersect when we do it graphically. That's all we're doing here. So this is just a word problem that reminds us to use that strategy of the natural log. I'm going to scoot over on this. You're going to want some space for this one, guys. So scoot over. Okay. So the natural log of x plus 10 minus the natural log of x equals the natural log of x plus 3. Okay, and so that doesn't look too bad. Let's use those properties now to simplify that to a single log on that side. It's a difference of logs, so that means it's the log of their quotient. The positive term is going to go on top. The term with the minus in front will go on bottom. Natural log of x plus 3. Okay, and what does that mean if the natural log of x plus 10 over x equals the natural log of x plus 3? That x plus 10 over x must equal x plus 3. Okay, so let's finish solving that. Go ahead and use those skills. Multiply both sides by x. We get x plus 10. X plus 10 equals x squared plus 3x. So 0 equals x squared plus 2x minus 10. And I'm not really sure why I picked to work this one other than it's going to, so are there factors of negative 10 that have a difference of 2? No. And so what are we going to do? quadratic equation. So that's just what I wanted to remind you, that we can use quadratic equation. X equals negative b plus or minus square root of b squared minus 4ac all over 2a. Okay, so you're welcome to sing with me. I like to sing it twice, once to set up the generic parentheses and then once to drop my numbers in. So x equals negative b plus or minus square root of b squared minus 4ac all over 2a. Okay, so I get negative 2 plus or minus the square root of something over 2. That something is going to be 4 squared plus 40, so 44. Is that what you got? Okay, that will totally, 44 will totally simplify under the radical. So that's going to be negative 2 plus or minus 2 on the square root of 11 over 2, which simplifies because every term has a factor of 2. So that's going to be 2 far. Negative 1 plus or minus the square root of 11. Is that what you got? Okay. All right. So let's approximate square roots. So square root of 11 is about, it's a little bit more than 3 because the square root of 9 is 3 and the square root of 16 is 4. And so it's between 3 and 4. So it's about 3, a little more than 3. So if we go back and look at the equation, okay, so here we go. Here's a plain x. That's always the easiest place to start plugging in. Negative 1 plus a little more than 3 is going to be positive. So we're okay there because that's positive. A positive plus a positive is positive. A positive plus a positive is positive. So the positive option works. When I do the negative option, negative 1 minus 3 is going to be negative. And can we have a negative? No. So we're going to throw out the negative option. And so we get x equals negative 1 plus the square root of 11. Negative 1 plus the square root of 11. Okay, all right, and let's try another one. So the next one says, let h of x equal log base 3 of 2x minus 3 plus log base 3 of x plus 4. Let k of x equal log base 3 of 8x plus 2. In the xy plane, what are all the x coordinates of the points of intersection of h and k? So that's just another example of the same. Do you guys need to do another example? I didn't think so. All right, let's keep moving along. Okay, so equations with multiple exponential functions. Oh, okay, so we did check our answers. Okay, so the nice thing is, like, you get in this habit of working logs and exponentials kind of together. Are there any restrictions on exponential functions? Are there any restrictions on my domain for exponential functions? No, the domain of exponential functions is all real numbers. So after getting used to checking your answers, then you hit these problems, you don't have to check because there are no restrictions on those, okay? But when in doubt, it never would hurt to check, right? Okay, so let's solve the following equations. It says when an equation has more than one exponential function, we can often solve the equation by, with simple exponential functions, finding common bases. Okay, so these are going to be simple, so let's see if we can knock these all 4 out real quickly. The first one's the easiest because they're already written with a common base. So again, this is not a mathematical operation that we're using to rewrite this, it's logic. If 2 to the 5x minus 1 equals 2 to the 2x plus 7, then what must be true? Logically, what must be true? The exponents must be equal. 5x minus 1 must equal 2x plus 7. So we use logic to set the exponents equal to each other, and then we just do a quick mathematical solving. So that's going to give me 3x equals 8, so x equals 8 over 3, and because it's an exponential, I don't have to check it because there are no restrictions that I'm worried about. Okay. On B, moving over to the right, what's the common base that this could be rewritten as? 2 cubed. So this is 2 cubed raised to the 3x minus 2 equals 2 to the x plus 5. So we want to simplify it to a common base. When we raise a power to a power, we multiply exponents. So this is 2 to the 9x minus what?
6.
Okay, the most common mistake I see here is people forgetting that you do have to distribute that to both terms. That's the most common mistake that I see there, is forgetting to distribute it, okay? It's that entire power raised to the power or multiplied by each other. And so that's just going to be equal 2 to the x plus 5 which if 2 to the 9x minus 6 equals 2 to the x plus 5, what must be true? Yeah, and then we just finish solving it real quickly. So that's going to give me 8x equals 11. So x equals 11 over 8. And it's an exponential, so I don't have any additional restrictions, and we're good to go. Okay, so let's just rewrite it. Do you guys think you can solve it if we finish rewriting it? Let's just practice. Well, let's just practice real quickly. Okay, so 9 and 27 can be rewritten to a base of 3. So let's do that real quickly. So that would be 3 squared to the 2x. And the 27 would be 3 cubed to the x plus 2. Okay, so that's going to give me 3 to the 4x equals 3 to the, good job remembering to distribute, okay? And if 3 to the 4x equals 3 to the 3x plus 6, what must be true? You got it, 4x equals 3x plus 6. So that means x equals 6. Okay, last one. 1/2 and 4 could both be written to a base of 2. This would be 2 to the negative first power raised to the 5x plus 7. And this would be 2 squared to the x. Okay, and I heard some of you were already doing it. It's true, when we raise power to a power, we multiply exponents, so that's 2 to the 2x. Okay, and this would be 2 to the, good job remembering the minus 7. Got to distribute to both parts. That just means negative 5x minus 7 must be equal to 2x by logic. So that means 7x equals negative 7, which means x equals negative 1. And then it's an exponential, so we don't have any additional restrictions, and we're good to go. Okay, I told you it would be fast. Y'all probably didn't need that many. It's so hard to decide when to skip. So now we're talking about solving. Okay, we're going to talk about inverses first and then inequalities. So inverses first and inequalities. Okay, so you guys remember that I told you they're going to want you to recognize this as the inverse form of this exponential. And it's okay if you don't like have that memorized, that that's the inverse form of it, because if you just do the steps to find the inverse, you're going to find that. You're going to find that. But if you do it enough or work with them enough, you'll start to recognize that, oh yeah, that's the inverse of it. That's the logarithmic inverse form of it. Okay. So now they just want us to do some where we have the bigger, more general form of a logarithmic function. So we've got the expanded exponential form or general form of an exponential, f of x equals a times b to the x plus h plus k, and the logarithmic function f of x equals a times log base b of x plus h plus k. So that's just where we're seeing all of the different things that could be transformations of the function, right? All the pieces where it could be transformations. And we're still just going to proceed with the same regular steps to find the inverse. We're going to switch the roles of x and y, use inverse operations to solve for y in the inverse relation, and write the final inverse function using the correct inverse notation. So it's just going to be the same process, but now with our rules for inverses and logs, for exponentials and logs. Okay, so it says find the inverse of the function 3 times 2 to the x plus 4 minus 15. Okay, so remember, f of x is just like y equals notation. So we're going to switch the position of x and y. So I'm going to rewrite this as x equals 3 times 2 to the y plus 4 minus 15. Everybody off to a good start? Everybody with us? Okay, and now we just want to solve for y. So let's start doing that. So the first thing we want to do is to both sides. So x plus 15 equals 3 times 2 to the y plus 4. Okay, next I want to divide both sides by 3. So x plus 15 over 3 equals 2 to the y plus 4. Okay, and now we need to rewrite it in logarithmic form. So that's going to be log base 2, because 2 is my base being raised to a power of, look at you guys, you're so good. You're so good. Equals, okay, and so last step to get y by itself, yep, and so that's going to be log base 2 of x plus 15 over 3 minus 4, okay? And then we said last step we have to rewrite it in the correct notation, so we're going to rewrite this as f inverse of x equals log base 2 of x plus 15 over 3 minus 4, okay? All right, so when I was going through my notes, I did it in the, I did it in this form with the variables and solved it, but it's not like an equation you're going to memorize. So I decided not even to show y'all in terms of a variable. You're just going to walk yourself through with the numbers and actually find the inverse. Was there a question? Shreya? No? It's okay. Remember, if you've got questions, you're never the only one who's wondering. So good students ask questions. So let us know if you've got questions. Okay. Do we need to do that again? I don't think so, but if you want to, there's another example there, and we're happy to do it if you want to. Okay, so let's look at number 3. It says, let h of x equal 3 to the x plus 1 minus 2. Let k of x equal h inverse of x. For what values of x does k of x equal 1? Okay, so this is just a question, like I'm just asking you guys. So what do you see and what are you thinking? Okay, we know k of x is really just h inverse of x. So this is saying, when does h inverse of x equal 1? Okay. And what do we know about the outputs of the inverse? They're the inputs of the original. So if we come back to the original and put in 1, that gives us 3 to the 1 plus 1 minus 2. 1 plus 1 is 2. 3 squared is 9. Minus 2 is 7. So the outputs of the original are the inputs of the inverse. So x equals 7. Kind of nice there. Kind of nice, huh? So it's about recognizing that when they ask you the question in that form, what you need to do to answer it. Okay, so it's just you saying you really do have the skills to answer that question. You've just never been asked the question in that way before. So it's about just kind of breaking it down and seeing what you can do with it. Okay, so that was kind of good to look at. Follow-up questions on that one? All right, so let's talk about inequalities. And here's where we're going to get to do some robust work. So we ready? All right, so previously we solved inequalities of polynomials and rational functions. To do this, we first found any x-coordinates where the function had zeros, holes, or vertical asymptotes. Then we used a sign chart and we tested each interval of the domain. Do you guys remember that? Okay, and so that's the same thing we're going to do with inequalities. They say it's even easier with inequalities. I don't know that I think it's easier, but it is the exact same process. So let's go ahead and try this. It says, let f of x equal log of x squared minus 4x plus 7 minus log of x plus 3. Where are all the values of x for which f of x is greater than 0? What are all the values of x for which f of x is greater than 0? Okay, so there's a couple things that we want to look at before we get started. So remember I said we could either look for the domain restrictions before we start, or we could check our answers at the end. For inequalities, we want to look at those domain restrictions at the beginning. The domain restrictions are going to be critical values along our number line that we're going to have to check. There will be additional critical values, but those are critical values that we have to check starting right off. Okay, so when I look at each part of this, what are my restrictions? So we know that x plus 3 has to be greater than 0, which means x has to be, what's the restriction here? X has to be greater than, so x, let me go ahead and write it. Sorry, I shouldn't skip any steps while y'all are new at this. So x plus 3 has to be greater than 0, which means x has to be greater than -3. So that -3 is going to be one of our numbers. So I'm going to start my number line over here. I don't know how many other numbers I'm going to have. Let's see. Actually, since let's talk about this for 1 second. Actually, I do know where to, well, maybe not, because y'all don't know the other numbers yet. But go ahead and put -3 over here, and I'll tell you why we're going to put it over here once we see what our other numbers are. But so you could just keep track of it. You maybe could just underline it as one of your numbers that you're going to put on your number line, okay, because we're going to have several. Okay, now if we go look at the next one, if we set that x squared minus 4x plus 7 equal to 0 and solve for it. Okay, it doesn't factor, so we're going to have to use quadratic equations. So x equals -b plus or minus the square root of b squared minus 4ac. Not nearly as much fun when we're not singing. All over 2a. Okay, so if I go look at that, to see what my restrictions need to be there, let me erase this extra space at the end. Okay, if I just look at the determinant, the number under the radical, I'm going to get 16 minus 28. 16 minus 28 is negative, which means it has no real solutions. You're right, that would be imaginary, but what that means is that there are no real solutions to where x squared minus 4x plus 7 equals 0. Okay, so it never is equal to 0, so that's not going to contribute no additional critical values there. It doesn't have any real solutions. It's not going to contribute any additional critical values. Okay, so we've got -3 is a domain restriction. Now we need to actually solve the inequality and see what our other restrictions, what our other critical values are based on the inequality. So this is a difference of logs. Well, let's go ahead and, this is a difference of logs. So let's go ahead and rewrite it as the log of the quotient, right? The log of the quotient. So that says the log of x squared minus 4x plus 7 over x plus 3 has to be, they want to know where this function is greater than 0. They want to know where this function is greater than 0. Okay, so all we've done is put an inequality symbol in where we would normally have an equal sign. So if I was going to rewrite that in exponential form, which is what I want to do right now, what's my base? Okay, so 10 to the 0 power, 10 to the 0 power, and 10 to the 0 is, maybe I'll go ahead and write that. Do you guys, we'll write that. Okay, so 10 to the 0 has to be less than x squared minus 4x plus 7. If you want to go ahead and write that 1 there, on the first time in the notes, I'm going to put that there so you see where it came from. So we're just rewriting this in exponential form. So 10 to the 0 is less than that. Okay, we said anything to the 0 power is 1, so this means 1 is less than x squared minus 4x plus 7. Ooh, that's kind of messy. Sorry about that. Over x plus 3. All right, let's finish solving that inequality. So I'm going to multiply both sides by x plus 3. That's going to give me x squared minus 4x plus 7 is greater than 1. And then, sorry, not 1, is greater than, thank you. X plus 3. Okay, and then I'm going to get that equal to 0, and that's going to give me x squared minus 5x plus 4 is greater than 0. Okay, so then we're going to just factor that. And that's going to give me factors of 4 that add to make -5, -4, and -1. Okay, and so what critical values does that give me? That gives me 1 and 4. 1 and 4. Okay, so this expression has to be greater than 0, so the critical values are where it would equal 0, and so that's at x equals 1 and x equals 4. So there's our 3 critical values. Now, we do not have to test to the left of -3. Can anybody tell me why we don't have to test to the left of -3? Our restriction said x has to be greater than -3. Our restriction said x has to be greater than -3. So I'm not boxing that as an answer. I was just kind of emphasizing, maybe put a little cloud around it. X has to be greater than -3. And so that's going to be an open parentheses, and we know that we're not going to use that section of the number line down there. X has to be greater than -3. Okay, so then we're going to test these remaining pieces. Okay, we're going to test these remaining pieces. So we're testing now. The restriction we're checking now is this equation right here. X minus 4 times x minus 1 has to be greater than 0. So a number between -3 and 0 that's easy to plug in. I said 0 because I was thinking 0. Between 1. Yes, 0 is the number that I would plug in. So we're plugging into the factored form. So 0 minus 4 is negative. 0 minus 1 is negative. Negative times negative is positive. Do we want positive? Yes, positive is greater than 0. So this section of our number line will work. Okay, can we use 1 and 4? We should have started with open circles and tried to decide whether or not we can include them. So can we include the values where it equals 0? No. So those are going to stay open circles. What was your question, Rishi?
Where are you plugging it into?
To this one right here. That's what this arrow is for. This is the restriction we're checking right now. The other was just a domain restriction. So this is what our equation simplified down to. So we were just solving our equation, our inequality, and our inequality simplified down to this. So we're just checking our inequality in its simplified form because that's easier than if we had to plug back in the original form. Okay, so a number between 1 and 4 that's easy to plug in? 2. Okay, so 2 minus 4 is negative. 2 minus 1 is positive. Negative times positive is negative. Do we want negative? No. So that section will not be shaded in. A number bigger than 4 that's easy to plug in? Okay, 5. 5 minus 4 is positive. 5 minus 1 is positive. Do we want positive? You betcha. And so this section is going to be included. Okay. And so the way they wrote up their answers, so this is AP Pre-Cal kind of notation, this is what we want you to say. We want f of x is greater than 0. And by the way, guys, if you're worried about like how to write it or how to say it, the answer keys that I post that are typed up, those are provided by people that are like high up in the process of the AP stuff. And so the way they say it is definitely an okay way to say it. So if you're wanting to check how to write it up and stuff, that's a good way to do it. So f of x is greater than 0 when you can, if you want to write it out in inequality form, it would be when x is between -3 and 1, or, and this is an inclusive or, which is the same. So an inclusive or is the same as union. That's the same as union. Okay. Or x is greater than 4. Okay. Now, most of us probably would prefer interval notation, and we'll write that in just a second because that's also true. Okay. And so that would be, we could say f of x is greater than 0 on the intervals -3 to 1, union 4 non-inclusive to infinity. Okay, so that would be a correct notation as well. But I do want you to see the inequality notation because they use it, and so I want to make sure that we understand it. In case it pops up or is an answer choice, we want to be good with that. Okay, all right, any questions about that? I say let's try another one of those, right? Because it was a little bit harder. So let's go ahead and try the one right underneath. Let's try number 5. So let g of x equal the natural log of x squared plus x minus 5, and let h of x equal the natural log of x plus 4. What are the values of x for which g of x is less than h of x, for which g of x is less than h of x? Okay, so let's go ahead and rewrite that equation. So we want g of x to be less than h of x. So that means the natural log of x squared plus x minus 5 is less than the natural log of x plus 4. Okay, now we want to rewrite that where it's equal to 0 so that we can actually solve it. So we're going to go ahead and subtract natural log of x plus 4 from both sides. So that's the natural log of x squared plus x minus 5. Now I'm going to show this in every step. I'm going to show every step of this so that I don't lose you guys. But did anybody have their mind start going as soon as we wrote subtract? Did any of you, your little algebra eyes start blinking? Okay, because what are we going to do with that subtraction? We're going to rewrite it as the quotient. The difference of logs is the log of their quotient. So that's the natural log of x squared plus x minus 5 over x plus 4. Okay, so my request from you is always to show the first step with no changes. So just write what the problem actually asked. And then as many or few steps as you want to show to simplify is fine. Okay. All right. So now this looks very much like the problem that we had just a minute ago. Let's start by getting our domain restrictions from the original problem. So looking at the original problem, from this we know that what must be true? X plus 4 must be greater than 0, which means x must be greater than -4. So we know that. Okay, so that's one of our restrictions. Okay, and let's take a look at the other restriction that we have from this natural log. We know that x squared plus x minus 5 has to be greater than 0 because the argument has to be positive. Okay, so let's see. Now that one is not going to factor, so we're going to have to use our quadratic equation. So x equals -b plus or minus the square root of b squared minus 4ac all over 2a. Okay, so if we simplify that, we get that x equals -1 plus or minus the square root of something over 2. That something is going to be, sorry about that. Let me move that out of the way. I think that's what's moving it. Okay. It's going to be negative. No, it's going to be positive 21. So it's going to be square root of 21. Okay. And 21 is prime. So that's not going to, or it's not prime, but it's 3 and 7. So it doesn't simplify under the radical. Okay, and so we know that our key values there, if we go ahead and break that down, so approximating square roots, so negative 21, perfect squares, we've got 4 squared is 16 and 5 squared is 25, so it's going to be between 4 and 5. So x equals negative 1 plus the square root of 21 over 2. If I was doing this without a calculator, then I'd say that's 4 and a little. So negative 1 plus 4 and a little is 3 and a little. Divided by 2 would be 1 and a little. But if I use a calculator, I can get a more accurate approximation. That's approximately 1.791 ... And we have to do x equals negative 1 minus the square root of 21 over 2. So again, that's a little more than 4. So negative 1 minus 4 and a little would be negative 5 and a little, divided by 2 would be approximately negative 2.5 and a little. If I was doing it without a calculator, with a calculator, I can see that it's actually negative 2.791. ... Okay, so the problem with this domain restriction is that we're not done with it. We need to look a little bit more closely at it. If this had been the entire problem from earlier in the year, if we just wanted to know the domain of this quadratic, then you would know that you had to go to your number line and you have to test those intervals. And that's still what we need to do to get the restrictions here, because we're still working off this restriction that x squared plus x minus 5 needs to be greater than 0. So if I've got negative 2.7 and positive 1.7, just truncating those just for numbers to plug into. We need to check those 3 intersections and see which ones work. So we don't want to include the ones where they're equal to 0, so those are going to stay open circles. If I plug in a number less than negative 2, like say I plug in negative 3 into this quadratic, and it didn't factor, so I can't plug into factored form, so I'm just going to plug into the original quadratic that we're checking for the restrictions on. Negative 3 squared is going to be 9 plus negative 3 minus 5. So 9 minus 8 is going to be 1, and 1 is positive, and 1 is positive, and we're looking for where it's greater than 0, so that section works. So we can do numbers in that section. Okay, and so that gives us a domain restriction that x can be less than, and that was our negative 1 minus the square root of 21 over 2. So that's that restriction. So x has to be greater than negative 4. X has to be less than negative 1 over the square root of 2 minus the square root of 21 over 2, which we said, I'll go ahead and put the decimal approximation here too. That's less than negative 2.7. Okay. And then if we take a look at that middle section, let's check that next section. A number between negative 2.7 and 1.7 that's easy to plug in. Let's try 0. So if I plug 0 into the quadratic here, that 0 squared is 0 plus 0 minus 5 is negative 5, which is negative. Is that greater than 0? It is not. So that section of the domain is not included. And so then if we check that last section, a number bigger than 1.7, how about we try 2, plugging into this quadratic. 2 squared is 4 plus 2 minus 5. So 6 minus 5 is 1, which is positive. And do we want positive? Well, we want greater than 0, so yes, we do. So that section will be included in our domain. So x can also be greater than, that came from negative 1 plus the square root of 21 over 2, which was approximately 1.7, 91 if we want to be a little more accurate. And then I could put the 791 here as well if we want at least 3 decimal places there. And it continues. Okay, continues. Okay, so let's take a look at those initial domain restrictions on our number line. So we can start looking at our total. We're going to get additional restrictions when we finish solving this equation. You thought we left it over here for good. We didn't. We're going to come back to it in a second, but we were finishing up our domain restrictions that we wanted to start with. So looking at these numbers that we have so far, we have negative 4. Okay, we have negative 4. We have negative 2.7. We have positive 1.7. Okay, so let's look at what we know so far before we go look at our additional things. We know that x has to be greater than -4. So all of these are open circles because these are when it equals 0. So none of those can be included. And it says x has to be greater than -4. So we don't even have to check this section below -4 because it can't be equal to that. Now these two numbers, these are values. It says x has to be less than -2.7. So it's got to be in this section, or it's got to be greater than the 1.7. So what that means is that x cannot be in this middle section, or it would not be in the domain of our natural log of x squared plus x minus 5. So those are strictly domain restrictions that we have so far. We know that it can't be less than -4, and we know that it can't be between those two numbers. It's strictly got to be less than -1 minus the square root of 21 over 2, and it's got to be greater than -1 plus the square root of 21 over 2. So those are just our domain restrictions from the get-go. Now let's finish solving the equation. So we're back over here working on the rest of this equation. Okay, right now it's in logarithmic form, so we're going to rewrite that inequality in exponential form. And so that's going to give me, that's e to the 0. E to the 0 is greater than x squared plus x minus 5 over x plus 4. Now we said anything to the 0 power is 1, so that just gives me x squared plus x minus 5 over x plus 4 is less than 1. Okay, now when we go to solve this inequality, if you look at the typed completed notes that are posted online on the calendar, they go ahead and multiply both sides by x plus 4. But remember that when we multiply, that when we're solving an inequality, if we multiply or divide both sides by a negative, it flips the inequality symbol. So in general, we want to be hyper careful about ever doing that, ever multiplying both sides by a variable in an inequality, because we don't know whether or not we're multiplying by a negative, and consequently whether or not we need to flip the inequality symbol. Now, the reason they know that they can do that, and the reason that's okay in the example they did in the typed completed notes, is because they know this domain restriction that we already know, that x has to be greater than -4. And if x is greater than -4, then this denominator is never negative. This denominator is never negative. So since this denominator is always positive, it is okay to multiply both sides by a positive, and we know that it won't change the answer. That's the only reason they can do that. I'm not going to show solving it that way, because in general, when you're solving an inequality, if it wasn't inside this if we didn't have the specific restriction, then we might not know that that was true. If it wasn't inside the logarithm, we might not have that restriction. And then I don't want you to do that in general, because in general, it would be a problem where we wouldn't know. So in general, we try not to, we wouldn't want to multiply or divide by a variable. Okay, so let's go ahead and take a look at this. How can we solve it then without multiplying both sides by x plus 4? So another valid option, which like I said is like a good way to remember in general, we can just subtract that 1 from both sides. So that's going to give me x squared plus x minus 5 over x plus 4 minus 1 is less than 0. Now, let's go ahead and rewrite that over the common denominator. So if I want to write that over the common denominator of x plus 4, I've got my x squared plus x minus 5. And what does 1 look like over x plus 4? It looks like x plus 4 over x plus 4, but we're supposed to subtract it. So it'll be negative x minus 4 over x plus 4. So that is my -1, and just combining that over a common denominator. So that's less than 0. Okay, then we're just going to combine a few like terms. That x and negative x cancels, and so that's going to give me, I'm going to move right down here. I'm just going to keep going down here on the page just because we need a little bit more room. So it's going to be x squared minus 9 over x plus 4 is going to be less than 0. Okay, x squared minus 9 is going to factor. We'd like it in factored form because then it's easier to plug in. So that's going to be x plus 3 times x minus 3 over x plus 4 needs to be less than 0. And so this is going to be the factored form that we're going to use as we try to go ahead and actually find our solution, see what our solution is. So we have these domain restrictions going on, okay? And then we need this inequality to be true. We need this inequality to be true. So we want to know where this expression, which is equal to our original function that we're solving, is less than 0. And so we're going to test in these interval. So we're not going to test this interval and we're not going to test that interval. We're just checking between these two. And okay, and we need to pick up a few more numbers here. Okay, so we want to check up the restrictions of this function. And so we already have the restriction where the denominator is 0. That x plus 3 and x minus 3 is going to give us negative 3 as a critical value for when this is equal to 0. So we want to check where it's less than 0. So we want to pick up those critical values where it's equal to 0. And so that would be at negative 3 and at positive 3. So we'll add those numbers on there as well. Okay, so we've got those additional critical values. Now we want it to be less than 0. At these two values, it'll be equal to 0. So we're going to put those as not included and leave them open and unshaded. So now we're going to have a few more sections to check. Okay, so these are going to be the sections that we're going to check. So again, I'm just shading in the areas that we're not going to check that section, and we're not going to check that section because of our domain restrictions from the original expressions. Okay, so let's check these we are going to test, and let's check them in this factored form. So we're going to check in this factored form here. Okay, because that'll be the easiest to plug into. So a number between negative 3 and negative 4, maybe negative 3.5. Okay, so negative 3.5 plus 3 is a negative, times negative 3 minus 3 is also negative, over negative 3.5 plus 4 is a positive. So negative times negative is positive, so that's a positive over a positive, which is positive. Okay, is a positive number less than 0? We're checking for this number here, less than 0. No, it is not. So we're not going to include that section either. Okay, so let's check a number between negative 2.7 and negative 3, so maybe negative 2.8. Again, plugging into this form. So negative 2.8 plus 3 is going to be positive, and negative 2.8 minus 3 will be negative, and negative 2.8 plus 4 will be positive, and a positive times a negative is a negative, over a positive is a negative. Are negative numbers less than 0? That's what we're checking. Are they less than 0? And yes, they are. So we're going to shade that. So phew, finally we have some answers that are going to work. Okay, we're not checking that next section, so we're moving on over to looking for a number between 1.7 and 3. So the next number I'm going to check, let's go ahead and check 2. So if I plug in 2 plus 3 is positive, 2 minus 3 is negative, 2 plus 4 is positive, so positive times negative is negative, over a positive, which is negative. Do we want negative? Negatives are less than 0, so that is what we're looking for. So we'll shade in that section of our domain. And then we're going to check a number bigger than 3. So let's check maybe 4. 4 is easy. Okay, so 4 plus 3 is positive. 4 minus 3 is positive. 4 plus 4 is positive. So that's definitely positive. Are positive numbers less than 0? No, they are not. So we will not include that section in our final answer. So the answer to our question that we now have is that g of x is less than h of x when x is between negative 3 and what is the real number that negative 2.7 represents? It's the exact value was negative 1 minus the square root of 21 over 2. Negative 1 minus the square root of 21 over 2. Let's see if I can get a micro eraser to separate that negative. So, nope, I got a highlighter. So that we can tell that that's a negative minus the square root of 21. So negative 1 minus the square root of 21 over 2, or, because that's our inclusive or our union, x is between, what does that 1.7 represent? It represents negative 1 plus the square root of 21 over 2 and positive 3. Okay, so there's our final answer. Whew, we are working over here. All right. So one thing I do want to point out, like I said, they showed there's always more than one way to work a problem. They showed just multiplying both sides here in this step by x plus 4. The only reason I didn't do that is just because best practices in general, if this was just a plain inequality, you would not solve it that way. The only reason they were legal to do it is because they knew that the denominator was always going to be positive. And sure enough, if you look at our denominators, they are always positive because we already have the domain restriction that x is greater than -4. And so we never run into the options where that would be negative. But I did go ahead and show it just as a routine because in general, you just want to remember with inequalities that you don't know whether that variable would be positive or negative in general. And so best practices, we just don't do that. Okay, I hope this makes a little more sense. Let me know if you have any questions. Okay, and let's take a look at this last one real quickly. It says let k of x equal 1 minus 4 times 2 to the x minus 3. What are the values of x for which k of x is less than or equal to -31? So that literally means we just want this expression 1 minus 4 times 2 to the x minus 3 to be less than or equal to -31. Okay, so let's start solving that. We remember that if you multiply or divide both sides of an inequality by a negative, you have to flip the sign. So we're just keeping that rule in mind before we get started. So I'm going to subtract 1 from both sides. That gives me -4 times 2 to the x minus 3 is less than or equal to -32. Next step, I'm going to divide both sides by a -4. So that means I have to flip the inequality sign. So that's going to give me 2 to the x minus 3, flip that inequality sign, equals -32 divided by -4 is going to be +8. And then I'm like, this is an exponential and it's an easy one. I can actually rewrite this with a common base. So I'm going to do that. So 2 to the x minus 3 has to be greater than or equal to 2 cubed. So if 2 to the x minus 3 is greater than or equal to 2 cubed, what does that mean? It means x minus 3 has to be greater than or equal to 3. Add 3 to both sides, and I get x has to be greater than or equal to 6. It's an exponential, so it doesn't have any restrictions, so we are good to go.